Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. I have been discussing about image features. After image features, the next step is image classification, image recognition. So for this, I have to apply pattern classification or pattern recognition algorithms. The machine learning algorithms I have to apply for object recognition, object classification. So now I will discuss some fundamental concepts of machine learning, pattern classification, and it is not possible to discuss all the machine learning concepts in this computer vision course. So that is why I will discuss briefly some important concepts of machine learning, and after this I will discuss some of the applications of computer vision. So for pattern classification, there are mainly three approaches. One is the statistical approach, one is the structural approach, and one is the soft computing based approach. In statistical approach, we will consider some statistical methods, and based on this we can do pattern classification, pattern recognition. Another one is the structural method, that is nothing but description of a particular pattern. And finally, the soft computing based pattern recognition. In this case, we can use fuzzy logic, artificial neural networks, genetic algorithms, and genetic programmings. So I will mainly discuss only the statistical pattern recognition techniques and also the soft computing based pattern recognition techniques. But all the concepts I will be discussing in brief. So let us see what is pattern recognition. So in my first class, I discussed about this block diagram. This is a typical computer vision system. So first one is the image acquisition by camera, and after this we have to do some pre-processings, and final step is the feature extraction and the pattern classification. That is nothing but decision making. So pattern recognition and the artificial intelligence algorithms. So already I have discussed about image features. So different features like color feature, texture features, shape and the boundaries like this we have discussed. So now I will discuss some pattern recognition concepts which are mainly used in computer vision applications. So this block diagram also I have shown in my second class, and that is the image analysis system. You can see input images are available, and after this we have to do some pre-processing. After pre-processing we have to do feature extractions. So here you can see I have shown the feature vector x1, x2, xn. These are the elements of the feature vector, and after this we have to go for classification, that is the object classification, object recognition. And you can see the domain of that machine learning. The first one is the artificial intelligence, the programs with the ability to learn and reason like humans, and that is the artificial intelligence. And you can see the machine learning is a subset of artificial intelligence. So algorithms with the ability to learn without being explicitly programmed, that is machine learning. And if you see the deep learning is a subset of machine learning, and in this case we use the artificial neural networks and also the deep networks. So this is about the machine learning and the deep learning. And in this case there are some applications of pattern recognition, machine learning, and in this case I have shown the machine perception for speech recognition, fingerprint identification, optical character recognition, DNA sequence identification, biomedical image processing, and biomedical signal processing. So build a machine that can recognize different patterns. So these are the examples. So I can give one example of human perception. So we can recognize all the alphabets of the English language. So for this we train ourselves to recognize different alphabets, and whenever suppose the new alphabet is coming or it is available, we can recognize based on this learning. And in this case we have the memory and the intelligence in recognizing the alphabets. This is one example of human perception. Now next one is the machine perception. So how about providing such capabilities to machines to recognize alphabets? So in this case also we have to do training the machine And after this, the machine can recognize different alphabets. So first thing is the training, and after this the testing. So for pattern recognition, I have to define some terms. The first one is the pattern. So I can give one example of the pattern. The pattern may be signal or maybe object. So if you see the definition of the pattern, so a pattern is an object, process or event that can be given a name. And after this, next one is the pattern class. So a pattern class is a set of patterns sharing common attributes and usually originating from the same source. So suppose the fingerprint is a pattern, and suppose if I consider the fingerprint of school employees, then that is the class, the pattern class. So my pattern will be the fingerprint, and if I consider the pattern class, that is the fingerprints of the school employee, particular school employee, if I consider, that is the pattern class. After this, the recognition. So during recognition or classification, given objects are assigned to prescribed classes, and for this we consider classifier. So this is about the pattern classification. So first I have to understand the pattern, and after this the classes, the pattern classes. After this, what is recognition and the classification, and what is classifier. Some of the pattern classification examples are like optical character recognitions, even in the biometrics and the face recognition, fingerprint recognition, speech recognition, machine learning is used. And for medical diagnosis, the X-ray imaging, ECG analysis, there are many applications of machine learning, pattern recognition, and also applications in military. So the approaches are statistical pattern recognitions. So it is based on underlying statistical model of patterns and the pattern classes. So statistical techniques will be used for statistical pattern recognition systems. So mainly I will discuss about the statistical pattern recognition systems. The next approach is the structural approach. It is nothing but the description of a pattern. So suppose if I consider the pattern A, so A I can consider like this. A has 3 primitives. If you see, the A has 3 primitives. So by using these structural components, I can represent the pattern A. This is about the structural pattern recognition system. Nowadays it is not much of use. So that is why we will discuss statistical pattern recognition and also the soft computing based pattern recognition. The next approach is the soft computing based. Here I have shown the neural networks, but it is the soft computing based pattern recognition. Soft computing based pattern recognition. So for this we can use fuzzy logic, artificial neural networks, genetic algorithms and the genetic programmings. So these are the approaches of pattern recognition. Now I will show one typical block diagram of a pattern recognition system. So for this you can see I have suppose patterns. After this we have to do some measurement. And we have the measured values. After this we have to extract features. So after feature extraction we will be getting the feature values. So all the features are not important, so that is why we are considering feature selection. And after feature selection we will be getting the feature vector, we will be getting. So feature vector is suppose x. X is the feature vector. So after getting the feature vector, what I can consider a classifier. So input to the classifier is the feature vector, and suppose we have a database, and suppose some rules are available, and after this what is the output? Output is the classify. That is nothing but the decision making. So if you see this typical block diagram of the pattern recognition system, so we have the input patterns, and after this we have to do some measurements, and I will be getting the measured value, that is nothing but the feature extraction. So I will be getting the feature values. After this, all the features are not important. So what we are considering, we are selecting some of the important features, that is the discriminative features we are selecting, that is the feature selection, and after this we are getting the feature vector. The feature vector is X, that is inputted to the classifier. So you can see the classifier, and we have the database, suppose that is the training samples are available, and some rules are available, and based on this we can do pattern classification, we can do decision makings, and these decision makings may be the hard decisions, or maybe the soft decisions. In case of the hard decision, we use classical set theory. And in case of the soft decision, we consider a fuzzification, that is the fuzzy set theory is used. So we consider fuzzification. So one may be hard decision, another one is the soft decision. In case of the hard decision, we use classical set theory, and in case of the soft decision, we consider fuzzification, that is nothing but the fuzzy logic we can consider. So this is a typical block diagram of a pattern recognition system. And in this case, what is the hard decision and what is the soft decision? Suppose if I consider two classes, these are the classes, suppose the samples of a particular class, and this is another class, the samples of another class. And suppose this is a decision boundary between the classes. So I am considering the class 1, and suppose it is a class 2, and between class 1 and class 2 I am considering the decision boundary. So this is the decision boundary. Now in this case, in case of the hard decision, you can see I have the clear separation between the classes, the class 1 and the class 2. But if I consider the fuzzy decision boundary, the decision boundary will be something like this. And this is not rigid in case of the fuzzy decision boundary. So what happened? There is a possibility that a particular sample, suppose this sample, belongs to another class. In case of the hard decision, already I have shown the decision boundary. There is no possibility that a particular sample belong to another class. But in case of the soft decision, there is a possibility that a particular sample may belongs to another class. This depends on the fuzzy membership grid. So if you read the fuzzy logic, then you can understand one concept. That concept is the fuzzy membership grid. So based on the fuzzy membership grid, there is a possibility that a particular sample may belong to another class. So one is the hard decision, that is there is no possibility because the decision boundary is very rigid, and you will be getting the separation between two classes, the class 1 and the class 2. But in case of the fuzzification, in case of the soft decision, based on the membership grid, there is a possibility that a particular sample may belong to another class. It is based on the membership grid. That is about the hard decision and the soft decision. And how to represent the pattern classification problem? So I can show you what is the pattern classification. So for this, what I am considering a space. This space is the class membership space C I am considering, and in this case I am considering the class. Suppose the class is Wi, another class is suppose class Wj, and another class I am considering class Wk. So 3 classes I am considering, suppose. So that is the class membership space, and I have the pattern space. So pattern space is something like this. Suppose I have 2 patterns, one is P4 and another one is P, suppose 1, and another pattern space is P, suppose this is P2, and another space is suppose P3. This I am considering as the pattern space. This is I am considering as pattern space. And after this I am considering another space, and that is the measurement space. So corresponding to this I have 3 measurements, suppose M1, M2 and suppose M3. Okay. So each class Wi generates a subset of pattern in the pattern space. If you see the pattern space P1, P2, P3, P4, they are overlapping. That is, the meaning is patterns of different classes may share some common attributes. So in this case, if I consider a mapping, suppose, so corresponding to the class Wi, I have 2 patterns, the P1 and P4. Corresponding to the class Wj, my pattern is P2. Corresponding to the class Wk, now my pattern is P3. This is the mapping I am considering. So here you see the corresponding to the class Wi, I have 2 patterns, one is P1 and P4. Corresponding to the class Wj, I have the pattern is P2. Corresponding to the class Wk, I have the pattern P3. And you can see here the patterns of different classes may overlap. Why it is overlapping? Because the patterns of different classes may share common attributes. So that is why it is overlapping. And corresponding to these patterns, if I consider the mapping from the pattern space to the measurement space, so corresponding to the pattern P1, the measurement is suppose M1. Corresponding to the pattern P2, the measurement is M2. Corresponding to the pattern P3, the measurement is suppose M1. And corresponding to the pattern P4, the measurement is suppose M3. So this is the mapping from the pattern space to the measurement space. Now in this case, the problem of the pattern classification is I have the measurements. From the measurements, I have to determine the class, the corresponding class. So suppose the measurement is M1. So what is the corresponding class I have to determine? But in this case, it is not one-to-one mapping. If you see, it is not one-to-one mapping. That means from the measurement, I have to determine the class. That is nothing but the invert mapping. So I have the measurements, and from the measurements, I have to determine the corresponding class. But it is not one-to-one mapping. Had it been one-to-one mapping, then the pattern classification problem would have been very easy. Since it is not one-to-one mapping, then in this case, we have to apply some techniques. The machine learning techniques. That means from the measurement, how to determine the particular class. And this is nothing but the invert mapping, the mapping from the measurement space to the class membership space. So like this, I can define the concept of pattern classification. Statistically, I can represent this problem like this: the probability of Wj given x. So what is the meaning of this? So I have to find the probability of obtaining a particular class given the Fisher vector is x. X is nothing but the measurement. So from the measurement, I have to determine the particular class. So that is the concept of the pattern classification, and I have to determine this. So in pattern classification, I have to determine this probability. And in this case, there are two learning techniques. One is the supervised. In case of the supervised learning technique, we know the class levels and the corresponding training samples are available. Okay. So suppose I have the class Wi and corresponding to Wi, I have the training samples. That information is available in case of the supervised learning. And after learning, after training, we have to do the classification based on the trained model. That is the supervised classification. In case of the unsupervised classification, we don't know about the class levels. So what is available? Only we have the feature vector. So we have to group the feature vectors based on some similarity. So that is nothing but the clustering. So what we have to consider? We have to group the feature vector based on some similarity. That is the unsupervised. So later on I will discuss about supervised and the unsupervised. The main concept is that in case of the supervised, we know the class levels and also we have the training samples corresponding to a particular class. In case of the unsupervised learning, we don't know about the class levels, but the feature vectors are available. So we can group the feature vectors based on some similarity. That is about the unsupervised technique. And for classification, one mathematical representation is that we can define one function. That function is called discriminant function. This function is used for taking classification decisions. So this discriminant function is represented by GIX, that is to partition R to the power D space. So GIX is nothing but to partition R to the power D space. And in this case, I am considering I is equal to 1, 2, up to C number of classes. So for class 1, suppose I have the discriminant function G1x. For class 2, I have the discriminant function G2x, like this. So I have to determine the discriminant function, and after this I have to find the maximum discriminant function that corresponds to that particular class. So I have to determine the discriminant function for the class 1, for class 2, class C, I have to determine the discriminant function, and in this case I have to determine the maximum discriminant function that corresponds to that particular class. So the decision rule will be something like this. What is the decision rule? The decision rule will be like this. The feature vector X which is assigned to this particular class, the class is suppose Wm. When the Gmx is greater than Gix for I is equal to 1, 2 up to C, and I is not equal to M. So based on this condition, if Gmx is greater than Gix, then in this case, based on this, I can assign the feature vector to the class is Wm. And in this case, you can see the discriminant function is used to partition R to the power D space, that is the D-dimensional space, that is the feature space. Suppose if I consider the 2-dimensional feature space, the 2D feature space, so suppose x1 and x2, 2-dimensional feature space, and you can see this is the decision boundary I am considering, and corresponding to the class W1, the region is R1, and corresponding to the class W2, the region is R2. And here you can see this is the decision boundary. This is the decision boundary. It is nothing but G1 is equal to G2. G1 will be equal to G2. So in this case, what I have to consider? I have to determine a discriminant function corresponding to the class 1. And corresponding to the class 1, the region is R1. And corresponding to the class 2, the region is R2. So for class 2 also we have to determine the discriminant function. And this maximum discriminate function, the maximum, which one is the maximum, the Z1 will be maximum or maybe the Z2 may be maximum. Based on this, we can take a classification decision. And in this case, what is the equation of the decision boundary? The equation of the decision boundary is Z1 is equal to Z2. So, one important point is the decision boundary and the discriminate function. Here I have shown the components of pattern recognition system. So, already I have defined. So, we have the patterns. After this, we have some sensors for measurement, that is for the data acquisition, and after this we have to do some pre-processings. After this we have to extract some features. After extracting the features, we can select some important features, that is called the feature selection, and after this we have to go for classification. And in this case we have shown here learning algorithms we have shown, that is nothing but if I consider the supervised training, the supervised learning, the training samples are available for all the classes and we know the class labels, and based on this information we can train the classifier, we can train the system. So, this is about the components of the pattern recognition system. And in this case I have shown one example of pattern classification. Here you see the problem is the jockey and the hoopster recognition, and for this I am considering these two states, one is the H, another one is J, that is the two classes I am considering, and I am considering the two-dimensional feature space, and in this case I am considering two features, one is the height, another one is the weight. So, x is the feature vector and x1 is the height and x2 is the weight. I am measuring by using the sensor. So, the feature vector has two components, one is x1, another one is x2, that is these are elements of the feature vector. After this what I am considering the function qx. In this case what I am considering, this equation I am considering w dot x, that is the dot product between the weight vector w and the input vector, input feature vector is x, plus b is the offset I am considering. If it is greater than 0, then the corresponding class will be h, and if this w dot x plus b is less than 0, then the corresponding class will be j. So, based on this condition I am determining the class, particular class, that is the decision making I am doing based on these equations. And in this case you can see I am showing two classes in the figure. The red is the class j, so this is the class j, and the blues are the class h, and in between you can see the decision boundary. So, what will be the equation of the decision boundary? The equation of the decision boundary is w dot x plus b is equal to 0, and for this I have the training examples, the training samples are available. So, x1, y1, x2, y2 like this, the training examples are available to train the system, and after this we can find the decision boundary between these two classes. And in this case you can see based on this objective function, that is w dot x plus b is greater than equal to 0, I can decide the class h, and also if I consider w dot x plus b less than 0, then the class will be j. So, this is the example, one example I am considering. And for feature extraction, you can see here in these two figures I am considering good features and the bad features. In the first figure you can see I am considering two classes, one is the red, another one is blue. In case of the good features I can easily draw a decision boundary between these two classes, and this is a linear decision boundary. In case of the bad features, it is very difficult to find a decision boundary between the classes. So, here you see in the second example, in the second figure, it is very difficult to draw the decision boundary between the classes. So, it is very difficult to draw the decision boundary between the classes. So, these are the examples of the bad features. So, that is why the feature selection is important. So, suppose I have the feature vector, the dimension of the feature vector is suppose n dimension x1, x2, xn. So, all the features may not be important. So, that is why I have to reduce the dimension of the feature vector. So, I can reduce the dimension of the feature vectors by some methods. So, one method already I have discussed, that is the PCA, the principal component analysis. So, you can see n is greater than m. So, I can reduce the dimensionality of the feature vector. So that is called the Fisher selection. And one issue is like this. Suppose if I consider, suppose D is the dimension of the Fisher vector, and if I consider this accuracy, this side. So if I increase the dimension of the Fisher vector, initially the accuracy will increase, and after if I increase the dimension again, the accuracy will drop like this, because if the number of training samples are limited training samples are available, and if I increase the dimension of the Fisher vector, that may not increase the accuracy may decrease. So that is why Fisher selection is important. Because of the high dimension, the accuracy drops, and this is called the curse of dimensionality. If I increase the dimension of the Fisher vector, the accuracy may not increase, it may drop, and this is called the curse of dimensionality. So we have to reduce the dimension of the Fisher vector. So that is why the Fisher selection is important. And in this case, I have shown the classifiers, and also you can see the regions x1, x2, x3 corresponding to different classes. So suppose the class W1 corresponding to W1, the region is x1, corresponding to W2, the region is x2, like this I am considering. And first case, if you see the first figure, that is the linear decision boundary I am getting between different classes. And if I consider the second figure, in the second figure I am not getting the linear decision boundary between the classes. So you can see x1, x2, x3 like this I am considering. So in the first case I have the linear decision boundary, and in the second case I am not getting the linear decision boundary. And here you can see x is nothing but x1 union of x2 union of like this. So this is the total space, that is the Fisher space. And this concept already I have explained. So here you can see the input is the Fisher vector here, and corresponding to this Fisher vector I am determining the discriminant functions g1x, g2x, g3x like this. For all the classes I have c number of classes, and I have to determine the maximum discriminant function. So suppose g2 is maximum, that means the corresponding class will be 2. So based on this discriminant function I can do the classification. So based on the discriminant function I can do the classification. And later on I will discuss about the Bayesian decision theory, that is mainly on the Bayes law. And in this case I will be considering two measures. One is the probability of the error, so probability of error also I can determine, and also the risks also I can determine in case of the Bayes decision theory. And based on these two measures, one is the probability of error, another one is the risks, I can take a classification decision. So what is risks? Risks of taking a particular action. So I have to take some actions, and I have to determine the risks of taking these actions, and I have to determine the conditional risks, and based on the conditional risks I can decide a particular action, and also the classification decision I can take. So by using these two measures, one is the probability of error, another one is the risks, I can do the pattern classification. And in this case, in case of the Bayes law, these are the terminologies. One is the class are represented like this, W1, W2 like this. So in this case I am considering two pieces, one is the C bus, another one is the Salmon. And in this case I am considering the prior probabilities. The prior probabilities are PW1 and PW2, these are the prior probabilities. And we have the evidence, and that is the Px. So if I consider the Bayes law, the posterior probability is equal to prior probability into likelihood divided by evidence. So this is the Bayes law. Evidence has no significance in classification. It is nothing but the normalizing factor. So based on the information of the prior and the likelihood, we can take classification decision. So here you see I am showing the Bayes rule, that is the posterior probability you can see is equal to the likelihood into prior divided by evidence. The evidence is nothing but the scale factor. So if you see the evidence is nothing but the scale factor that is used for normalization. So in classification it has no significance. So based on the parameters, the parameter is likelihood and the prior, we can take classification decision. So let us consider these decisions. So decide a particular class W1 if the probability of W1 given X is greater than probability of W2 given X. Otherwise, we can decide the class W2. So this is based on the posterior probability, the posterior density. Similarly, if I consider this likelihood and the prior, so this is the likelihood and this is the prior, that based on this I can decide a particular class. If the probability of X given W1 into probability of W1 is greater than probability of X given W2 into probability of W2, then I can decide the class W1, otherwise I can decide the class W2. And in this case, we can define the term is the likelihood ratio. So from this I can determine the term the likelihood ratio. If the likelihood ratio is greater than a particular threshold, then in this case the corresponding class will be W1, otherwise we have to decide the class W2. So based on the Bayes law, I can do the classifications. You can see in case of the basic pattern recognition framework, we need the training samples, we need the testing samples, and also the algorithm for recognizing unknown test samples, and we are considering the supervised learning. That means we know the class levels and corresponding to all the classes we have the training samples. So we are considering the supervised learning. And in this case, one problem is suppose alphabet recognition. So 26 alphabets are available, uppercase. So for this what we have to consider, collect the samples of each of the 26 alphabet and train using an algorithm. So first we have to collect all the training samples of the alphabet. And how many classes? We have 26 classes because we are considering 26 alphabets, uppercase alphabet. After training, what we have to do? We have to do the testing using unknown samples. That is, the unknown sample means unknown alphabets we have to consider. And after this we can determine the accuracies. So this is the typical supervised pattern recognition problem. And what are the patterns? Already I have defined what are the patterns. The patterns may be a signal, or maybe the fingerprint image, handwritten word, human face, speech signal, DNA sequence, alphabets, like this. These are the examples of the patterns. And in this case I have shown one example of the handwriting recognition. So for this also we have to extract the features, and based on these features we can recognize the handwritings. And this is another example, the face recognition. Here you can see, if I consider the first row, the same face but different lighting conditions and different poses. In this case also we have to recognize the face. So for this also we have to extract the features, and based on these features we can recognize that particular face. In the second row also I have shown the face of a lady, and in this case you can see different poses and different facial expressions and also different lighting conditions. So for this also we have to recognize the face. And this is another example, that is the fingerprint recognition. So in this class I discussed the concept of pattern classification, and also I have shown one mapping diagram. So in the mapping diagram you can see from the measurement I have to determine the classes, the corresponding class I have to determine. So the feature vector is available and I have to determine the corresponding class. Statistically that is represented by probability of Wj given X. That is the definition of pattern recognition, pattern classification. In my next class I will continue the same discussion. So let me stop here today. Thank you.